Welcome to the Explainer. Today, we're diving into a really fundamental computer science concept that's quietly running behind the scenes of, well, almost every piece of everyday software you use. Whether you're prepping for an IBDP exam or you're just kind of wondering how your software actually ticks, this is a really fun one to figure out together. Let's get into it.
I want you to just think about this for a second. How does your computer know exactly what to undo when you make a mistake? You're typing up an essay or drawing some digital art, you accidentally hit delete, you mash that undo button, and, like magic, your last action is completely reversed. But it's not magic, right? How does the system actually remember? Well, the elegant mathematical solution that makes this whole thing possible is a data structure known simply as a stack.
Okay, so here's our roadmap for today's Explainer. First, we'll cover the LIFO concept. Then, the 4 core stack operations. After that, we'll look at speed and memory usage. Fourth, when to use stacks, and we'll wrap up with a Python stack implementation.
All right, jumping right into Section 1, the LIFO concept explained.
Before we start manipulating any data, we really need to set the ground rules. A stack is basically a collection of data where access happens at one end only. We call this end the top, and it strictly follows something called the LIFO rule. LIFO stands for last in, first out. This literally means that the most recently added item is absolutely the first one to be removed. So the really crucial takeaway here is that this mechanism makes stacks completely perfect for any time a program has to reverse order or just needs to remember its most recent steps.
To really anchor this abstract concept in reality, I want you to imagine a physical stack of dinner plates in a cafeteria. Say you're building this stack yourself. Plate 1 gets placed down first, right at the very bottom. Then plates 2, 3, and 4 get stacked one by one on top of it. Finally, plate 5 goes right at the top. Now, if you walk up to grab a plate for your lunch, which one are you taking? You're definitely not pulling plate 1 from the bottom unless you want a massive lap full of broken porcelain. No, you grab plate 5. The rule is super simple and intuitive. You must remove the top plate first. The last plate in is the first plate out.
Moving right along to Section 2, 4 core stack operations.
So we have the concept down, but now we need the specific commands to actually use this thing. In computer science, we interact with this stack using 4 fundamental operations. First up is push, which just adds a new item to the very top of the stack. Next is pop, which removes and returns that top item. Then we have peek, which reads the top item without actually removing it. And finally, isEmpty, which is a really simple check to see if the stack has absolutely no items in it. Now, I really want to emphasize the difference between pop and peek here. Pop takes the item completely off the stack. It's like grabbing that top dinner plate and walking away with it. Peek, that's just looking at the top plate to see what color it is, but leaving it right where you found it.
Let's actually test this out. I'm going to give you a sequence of 6 operations, starting with a totally empty stack. Treat this as a little mental puzzle to trace along with me. Take your time, visualize it. Step 1, we push the number 8. Step 2, we push 3. Step 3, we peek. Step 4, we pop. Step 5, we push 5, and Step 6, we pop again. Okay, hold your mental image of what the stack looks like right now. Got it?
Let's walk row by row and see if you nailed it. In Step 1, pushing 8 leaves us with a stack containing just an 8. Step 2, pushing 3 puts 3 on top, so our stack is 8, then 3. Now, what's really interesting here is Steps 3 and 4. In Step 3, we execute a peek. The stack stays exactly the same, 8, then 3. But it outputs the value 3 because 3 is the newest item resting right at the top. Then, in Step 4, we execute a pop. This completely removes the 3 from the stack, dropping us back down to just the number 8, and it outputs that 3. That is exactly why both peek and pop output the number 3, but only pop actually alters the stack. Moving on, Step 5 pushes 5, making the stack 8, then 5. And finally, Step 6 pops, outputting the 5 and leaving our stack with just the 8 again.
Let's dig a bit deeper. In Section 3, speed and memory usage.
Time to look under the hood. For those of you taking exams, just knowing the operations isn't going to cut it. You really need to understand the performance side of things. When we talk about speed in computer science, we often use big O notation. And the beautiful thing about stacks is that push, pop, peek, and isEmpty all operate at an instantaneous big O of 1 speed. That means constant time. Because a stack completely avoids having to search through every single element and only ever interacts with the one item sitting right at the top, normal operations are incredibly fast.
But you gotta remember, that speed comes with memory implications.
Every single stored item uses memory. If you're using a dynamic implementation, your stack can grow larger and larger as it needs more space. This means that very deep stacks can consume some really heavy amounts of memory. There's also an important distinction to make here. The stack data structure we code isn't exactly the same as the call stack used by your programming language's runtime, but they do follow that exact same LIFO idea. I have to warn you, if a recursive algorithm makes too many function calls, that call stack is going to keep growing and growing until your memory completely runs out. Fun fact, actually, this exact memory crash is literally where the famous programmer website Stack Overflow gets its name.
All right, Section 4. When to use stacks.
Pivoting now from the theory to the application, let's explore exactly when programmers actually rely on this structure in the wild. Basically, stacks are everywhere. When you hit undo or redo in a text editor, the software uses a stack, because the most recent action must be reversed first. When you click the back button in your web browser, it takes you to the page you visited most recently, right? So that URL is just being popped off the top of a history stack. In code editors, checking if nested brackets match up properly uses a stack, so the most recent opening bracket gets paired with the next closing bracket. And, as we literally just mentioned, handling function calls and recursion relies on a stack to ensure the newest unfinished function call gets completed first. In every single one of these examples, the core requirement is identical. The most recent item must be processed first.
To really solidify this in your mind, let's contrast the stack with another super famous data structure, the queue. Doing this brilliantly illustrates the difference. Think about undoing your last drawing action. You absolutely need a stack for that, because the newest action must be removed first, last in, first out. But now, imagine people waiting in a ticket line. It would be insanely unfair to serve the last person who arrived first. For a ticket line, or for processing jobs sent to a printer, you use a queue, where the first person to arrive is the first one served. First in, first out. So you choose a stack specifically when you need the most recent item first.
Wrapping things up with Section 5, Python Stack Implementation. Let's bring all this theory together by actually turning these concepts into code. Now, Python doesn't actually have a built-in stack type out of the box, but Python lists can behave exactly like stacks. We start by creating an empty list called stack. Then we use .append a. In list terms, append adds to the end, which perfectly mimics our push operation. We push A, then we push B. To do our peek operation, we use stack bracket -1 to print the last item in the list, which outputs B without removing it. Next, we use Python's built-in .pop method. It magically removes and returns the last item, just like a true stack pop, so it grabs B. Finally, checking if the length of the stack equals 0 is our isEmpty check. Here it evaluates to false, because A is still resting safely at the bottom of our stack.
Before we completely wrap up, let's look at a few common traps that are super easy to fall into, especially if you're taking a test. Number 1, mixing up LIFO with FIFO. Remember, stacks are last in, first out. Queues are first in, first out. Number 2, mistakenly thinking pop removes the oldest value. No way, it always removes the newest value. Number 3, forgetting the peek does not remove the top item. It literally only looks at it. And finally, number 4, describing how a stack works perfectly, but completely ignoring its effect on performance and memory. You gotta mention both.
And if you are sitting for the IBDP exams, here is an absolute golden sentence to keep in your back pocket. When you're asked to justify choosing a stack for a specific problem, just write, "A stack is suitable here because the most recent item must be processed first." That clear, concise phrasing shows the examiner you completely grasp the defining characteristic of a stack.
So, we've covered the rules, the operations, the performance, the real-world uses, and even the Python code. To conclude this explainer, I am leaving you with a final, provocative little activity to test your new mastery. I want you to mentally trace this exact sequence: push 4, push 9, pop, push 2, and finally peek. Ask yourself, what exact values are output during this sequence? And critically, is the stack empty at the end? Run through the steps, visualize that LIFO plate analogy, and see if you can solve it. Keep testing yourself, keep asking questions, and definitely keep coding. Thanks so much for joining me on this explainer.